Cool. Okay, we're getting a number of our classmates signed in. This is great. Welcome, Andrew. William.
Hey, how's it going?
Christian, welcome. This is great.
How's everybody doing?
How is everybody doing?
Good, good.
Cool. All right, and that's it there. Okay, so she's coming on also. Nice. So while we're waiting for a few more classmates to sign in, I had a question for all of you. Did you get my message yesterday regarding MultiSIM?
Okay.
Email message yesterday regarding MultiSIM. Did you check for email messages yesterday?
Yes, I did, and it took quite a while to download.
It does, but were you successful in installing it and getting it to run?
I was a bit ambitious. I was able to select pretty much everything I can download. So now it's probably why it's taking forever.
Okay, so MultiSIM.
I didn't get anything from the MultiSIM.
Yeah, likewise.
Likewise, what?
I only got this email for this one. I only got the email for this one. I didn't get nothing for the MultiSIM.
Okay.
I got the email for this one and 55B, and that's it.
Okay. And in 55B, was there mention of MultiSIM in there?
Let me double check.
Second half of the message.
Oh yeah, multi-SIM download. Okay.
So that means we've got to read the messages all the way through, yeah?
Correct.
Okay, so let me check here because that just came about last night. And
so it's also on the 50. You just got to scroll down.
it is also on the 50. So yeah, Andrew, do check that email, because if you've got the email for the Zoom, for the link, there's an also, and it says free 6-month MultiSIM download.
Okay, yeah, I see that. I see that underneath it now.
Okay, so 2 people are not reading the messages all the way through. If you were employees, you'd be in trouble right now, okay? So it's your responsibility to take this, the role of the student as if it were a job. And if your supervisor sends you something, you don't read half the message and then get on the Zoom call with your supervisor and say, what MultiSIM? I didn't remember seeing nothing about the MultiSIM. So anyway, consider your hand slapped, okay? Boom, boom, boom. Andrew, watch. There, your hand's been slapped.
Oh, my hand.
Oh, yeah, one of those too. Or maybe upside the head. Oh my goodness. Anyway, Nabil was able to contact our friends at MultiSIM and gave us this link which says there's a free 6-month evaluation, which is more than enough time for their LabVIEW and MultiSIM. It's actually 2 pieces of software. One is LabVIEW and one is MultiSIM. The MultiSIM part is the part that we have the most interest in playing with. And MultiSIM, it has been what we've been using for years. It's a bit more robust than the TINA TI. The TINA TI is great for everything that we've done so far. But as we're transitioning into capacitors, inductors, and more AC circuits, the MultiSIM will be a more advantageous piece of software to use with respect to those types of circuits, okay? So that being said, and Christian, I need your camera. Rebecca and Pauline need your cameras on as well. The dean has asked for all of us to have screenshots of our students' smiling faces in our class meetings. So let me go ahead and mark off who I have so far. I have Andrew. Is Kyle with you? today? You got your mic muted. There he is. How you doing, Kyle? All right. Okay, Pauline is here, and Gabe Orozco is here, and Rebecca's here, and 1, 2, 3, 4, 5. Christian is here. Cool. And let's see if anybody else signs in a little bit. Hopefully do, and we shall see. So give you a heads up on a couple of things that we're going to be doing today. We're going to continue on series parallel, and we're going to give you a different kind of series parallel circuit. If we go to, hey, you should have Canvas on in the background, and let me get Canvas on in my background as well. Here, and go to here, go to here. Nice, and move this up to here. Good, and do this, and do this, and go to here. In our week 3, well, in our week 11, I'm sorry, for all my other classes, we're into week 3. In our week 11, you'll see that we have capacitors as a primary topic. There happens to be some lecture photos, and let me talk to you about our lecture photos. Let me get to here, make a slight change here, space, update. Okay, so what I'd like for us to look at will be this. All right, let me share the screen with you. All right, so you should be able to see week 11 lecture photos by Co. Is that on your screen now? Give me a thumbs up if that's what you see. Good, okay. And on here happens to be some discussions of various topics we're going to touch on today. One of them happens to be called superposition theorem, and I've got 3 different images regarding superposition theorem. It's a type of a circuit analysis that's next on our list. There also happens to be a series parallel analysis. I've got image 1, image 2, and image 3. And these make reference to a day 15, 18, and 19 e-bike lecture. Ignore the notation, but the fact that we're dealing with series parallel analysis will be pertinent to our discussion today as well. And then there's also a lecture image regarding filters. So why don't we continue with our series parallel analysis? Let's go ahead and do a particular guy. I'm going to open this guy up, and it will download. It's a PDF that I created using OneNote. So I did these here. And let me walk you through this. And then after walking you through this, then we'll also do a circuit analysis together. So this is a series parallel, or is this a parallel series circuit? What can you see in here that you can identify? The key thing was look at the voltage source. And do I have a wire on the bottom of the voltage source going out? And then it goes to a node, yes? To node B. And as it goes to node B, you can all unmute your microphones, that's fine. Unless, yeah, perfect. Yeah, so I'm looking for some responses. So I have a wire coming out of the bottom of the 16-volt source. It is attached to a ground symbol, and the ground symbol is simply a common reference point. And then I have a wire coming over to node B. And what happens at node B? It looks like I've got a split between 2 wires. So it looks like I might have a possible parallel arrangement at the bottom of the circuit at point B. Take a look at the top of the schematic. The top of the schematic shows a wire coming out of V1 going into a 750 ohm resistor, and then it attaches to point A. And at point A, I've got 2 wires, so it looks like I got a split up there. So immediately attached to the voltage source is not a split on both sides. I only have a split on one side of the voltage source. On the other side of the voltage source, I have a series component. And because I have a series component, this is fundamentally, the first word we would use is that this is a series something circuit. Now, what that something works out to be depends on what else we realize in the circuit. So as we've done in the past, our task is to do what? Simplify. And how do we simplify? We simplify by redrawing. And we redraw this step by step, ultimately to get to the simplest circuit possible. So I've said, if wherever your voltage source is, you want to put your eyeball on the part of the circuit that is farthest away from the voltage, and look at this wire. So as this eyeball is looking at this wire, what does it see, Andrew? Attached to that
You
wire.
see a negative. Oh, what do you mean?
What is attached to that wire that the eyeball is looking at?
You have a resistor up there.
Good. Yeah, I have a resistor R4. And
Yes.
is there anything else attached to resistor R4?
Yeah, you have the R3.
I have R3. So that's very good. So I got two things attached on that wire. So Gabriel, what is the relationship between R3 and R4?
They're in parallel.
R3 and R4. Parallel means, if you go back to the definition of parallel, parallel means that we have split currents between them. Are we splitting currents between 3 and 4, or are 3 and 4 in the same current path?
No, they're in the same current path.
So if they are, so that's what you need to noodle out. If they are in the same current path, what is with Bolito? My gosh, check your email. Email. Bolito. Let me just get this sent out to him. Hold on one sec. Okay, so yeah, R3 and R4 happen to be in series with each other. So if they are in series with each other, there's nothing else between them, yay?
Correct.
Except a piece of wire. So if these two components are in series, can we combine these two perhaps?
Yeah.
Yeah. So we have an R3 and an R4, 2K and a 5K. If we combine them together, we have something here called REQ number 1. REQ number
7K.
1. What's that? Somebody, if you had a comment or question, let me know.
No, I was doing the math. I said it was 7K.
Yes, you're right. It does work out to 7 kilo ohms. So REQ1, I wrote down in blue, is the sum of R3 plus R4, the 2K plus 5K, giving us 7K. So hold on just a moment. Our friend is having some challenges. So if he's not even on here yet, don't want to lose him. Lord, excuse me just one moment, my friends. Day Zoom meeting. Show meeting invitation. No, he's still not on with us yet. Copy this guy. And reply again. And send. Okay, so hopefully Rolanda will be with us shortly. All right, so we have a 7K ohm resistance here, and let's do manage. Okay, there's the participants, and maximize that. We should see them coming on in a moment. Anyway, all right, coming back to the circuit, R3 and R4 combine to REQ1. There's nothing else between point A, right up here on this wire, all the way through the wire, these through two resistors, all the way to point B. So have we taken care of everything on the right-hand side of the circuit, simplifying these two resistors into a single equivalent one? RA is still underneath RA, RB is still underneath, point A and point B are still stacked on top of each other as they were in the original circuit. I still have an R2 between A and B, so that stays here. But instead of having two resistors off to the side, I now have a single REQ. Again, if my eyeball is here in this particular part of the schematic, looking at this wire, what do I see? I see a single resistor, and the single resistor at 7K ohms is attached to point B at the bottom and attached at point A at the bottom. So if I move towards the voltage source, what's the next relationship I should be able to see?
Parallel?
Parallel between what and what?
Would be R2 and what's that? It'd be R4? REQ1, sorry.
Yeah, we will call it REQ1 because R4 has already been absorbed into REQ1. So R4 and R3 no longer exist in this middle circuit. They've been replaced by a single equivalent resistance. But yes, you're right. You notice that we have a parallel relationship between R2 and REQ1. And as we combine these two in parallel, we end up with something new called REQ number 2. REQ number 2 is defined by this equation, R2 parallel with REQ1. And if we go to pop in the numbers, or actually if I write it out, REQ2 is equal to R2 plus R2 in parallel with the open parentheses, R3 plus R4, close parentheses. If you go through and you do all the math here, between 3K on one side and 7K on the other side, how many ohms do we end up with? It's got to be less
10K?
than 3. No, remember this is in parallel.
Oh, my bad.
Yeah, so the parallel sum will never be greater than the lowest ohmic branch. So it's got to be less than 3K. And if you do the math right now. Don't just sit there looking pretty. Pull out your calculators. Crunch out the calculation. Make sure you know how to do this. Oh, we got a new college student in the background. Yay, a little person. So you have 3 exponent 3 reciprocal plus 7 exponent 3 reciprocal. Hit equal reciprocal one more time. You end up with 2.1 K ohms. How many people confirm? Raise your hands. Okay, all right. And as we go further down, what do we have as a relationship in this third diagram? So we've taken the circuit from first, second, now third. This third diagram has an REQ2 between points A and B. But between the voltage source and point A, we have what? An R1, 750 ohms. What is the final relationship between this R1 and REQ number 2?
In series.
They're in series. So could I combine them into a single resistance by doing what with the numbers? How do I find my R total?
Just add them, 750 to the REQ2 value.
Yeah, so I should end up with a 2.85 K ohms, yes? Which is what we have here, right? Everybody seeing this on my screen? Is this big enough on your screen? I can make it bigger.
You're fine.
Too big now.
I will rescale my screen so you can see everything. Rolando, there he is. Okay. So welcome, Rolando. And so when we go to combine them, we will have a single resistance, R total. And so if you had to write this out in the form of an equation, R total would be equal to what? R1 plus in brackets, R2 parallel with open parentheses R3 plus R4. And we use this notation to work the equation from the inside out. Didn't we add R3 and 4 together first? R3 and R4 were in series, and then put in parallel with R2, and then added with R1 to give us the R total. So once you have our total, do we have enough information with the 16-volt source to be able to determine what the current is? Yep. And that's the basis of starting. Once you have that current, and you should go ahead and confirm this and show me your calculations on your calculators. Take 2.85 k ohms and divide that into 16 volts. So 16 volts divide by 2.85 k ohms. So we should end up with the following calculation.
5.61.
Mm-hmm. And let me switch my camera source to go to here. And on my camera source here. So I stop the share for a moment and go to here. Speaker view. There's my calculation, okay? So I need for you to hold your calculations up to the calculator. 16 divided by 2.85 kilo. Pauline's is good. Rebecca's is good. Andrew and Kyle, that looks great. And Rolando's coming on in a moment. Christian, hold it at a slightly different. Gabriel, yours is good. Could you tilt yours, the top of yours back? There, okay, that's great. Dynamite, okay. And hopefully Rolando will be catching up with this in a moment and doing this calculation. Dynamite, this is very, very helpful. Okay, so that being said, let's go back to my share and see if we can do the rest of this analysis. So come back up to here and hit share. So the rest of this analysis is, if I do my VIR chart, I've got 4 different resistors and I have a calculated 2.85 k ohms, which was up here. I transfer this to here. I calculated 5.61 milliamps and I transfer this to here. How come my currents are not all the same? How come my currents are kind of across the board? How come my voltages are not all the same? Because part of this is in series, part of this is in parallel. The part that's in parallel will show parallel behaviors. The part that's in series will show series behaviors. So if we go back and we think about this, wasn't R3 and 4 in the original circuit in series with each other? And in the original circuit, it was. Let me go. So in the original circuit, my R3 and R4 were in series, so they should share the same current, yes? The current through R3 and the current through R4 should be the same. And what I happen to have here is, yes, the currents are in fact the same. How do we determine these currents and the rest of these voltages? Well, I think the best thing for us to do is I will hold the rest of this in Canvas for you to look at, and we'll actually do a series parallel analysis of this sort on paper with you. So let me go ahead and get that set up. Okay. Let's move this out of this way. Move this over to here. And change here. Let's go ahead here. And I think and static. Okay, let's go ahead and do this. All right, let me change the orientation. Is this upside down? Nope, this is correct. Let me raise this up a little higher. All right, so I have series parallel analysis. And let me move this out of the view of the screen. Put this over here. And do this. Okay. All right, I can see all your smiling faces and I can also see the paper in front of me. Get my calculator handy. And let's see, what kind of a circuit do I want to design for us today? How about we do this? It won't be dissimilar to the one that you've got on your screen. I'm going to do it this way. So I will have a point A, I will have a point B. We will go ahead and make this particular fellow 28 volts. We will go ahead and call this from left to right. Let's say this is an R1, this is an R2, this is an R3, this is an R4, this one is an R5. So while you're copying that, let me see if I can take us off of autofocus and make it static. All right, so that being said, let's go ahead and create my VIR chart. So I must have an R1, an R2, R3, R4, R5, and total. Okay. V, I, and R. Cool. All right, let me give you some resistor values. Let's go ahead and make R1 980 ohms. Let's go ahead and make R2 2 kilo ohms. Let's make R3 1.5 K ohms. Let's go ahead and make R4 330 ohms. Let's go ahead and make R5 equal to 770 ohms. So with that, we should have enough information to be able to put onto our document. So is the focus good that everybody can see the values? Okay, I will reiterate down here, my R1 is 980 ohms. My R2 is 2 kilo ohms. My R3 is 1.5 kilo ohms. My R4 will be 330 ohms. My R5 is 770 ohms. My starting voltage is 28 volts. There you go. Cool. All right. So what was the advice that I had given you on how to get this thing started? Where would we start our analysis?
On the opposite end of the voltage source.
Okay, my voltage source happens to be on the right-hand side. And so the opposite end of the voltage source is over this side. That being said, we need to put our eyeball on this side of the schematic. So let's go ahead and I guess that's an eyeball. Anyway, so we're looking at this particular side of the circuit. And as we look at this side of the circuit, what relationships do you see between components that are on this wire in this particular part of the circuit? Question goes to Rebecca. What do you see there?
R1 and R2 are in series.
Rebecca says R1 and R2 are in series. How many of you agree with that, or how many of you have a disagree with that?
I agree with that.
I agree.
Because what was the definition of series? Series means that there's a common current path, a single current path between these two components, yes? And so since there isn't any split between them, there is no split between them, they are truly in series. So that allows us to be able to combine these two into an equivalent resistance, yes? So again, our process is called circuit analysis. So the process is circuit analysis. Our method will be through redraw, several redraws, and purpose to simplify. So those will remain the same. Let me re-ink this. My other one was starting to get a little faint there.
Mom, my teacher said I can eat this. Yeah.
Circuit analysis. Cool. All right, so now we're going to redo this particular guy. And in the redraw, my recommendations are always to save some space below your original schematic and draw directly underneath your original schematic. And so I will retain point A. I will retain the original R3 at 1.5 K ohms. I will retain the original point B. On this side of the schematic, I now have a singular resistance. And the singular one is now called REQ1. And that was equal to R1 plus R2, which in this case works out to be 2.98 kilo ohms. Is that correct?
Yes.
And then on this side, we retain the original R4. We retain the original voltage source and the original R5. Okay. So now, again, the eyeball is looking at the circuit from this corner as far away from the voltage source as possible. So on this corner, the question now goes to Rolando. Mr. Bolito, so glad you could join us. On this wire that the eyeball sees, what do I see attached to this wire at this point?
Parallel with R3.
Okay, we see this resistor in parallel with R3 because the top of these resistances meet at a common node called A, and the lower leads of these two components meet at a different common node called B. So therefore, these two guys are in parallel. Very good. So we will go ahead and combine these two in parallel. And so I will do another redraw. I will bring in my original point A, my original point B, original voltage source, my R4, my R5, and now I have a new REQ, and we call this number 2, yes? REQ number 2. And REQ number 2 was REQ 1 in parallel with R3. And so that means we will have 2.98 K ohms in parallel with 1.5 K ohms. So that being said, just off the top of our head, can we guesstimate some kind of a number for this? Question goes to Pauline. The result of these two in parallel to be a single equivalent resistance should come up to approximately some kind of a number. What would that, might that be without calculating?
That would be 3.4 kilo ohms.
They're in parallel now. Do we?
Oh, I'm sorry.
Yes. What do we know about parallel resistance, total of a parallel bank? That this equivalent resistance must end up with a total resistance that must be
Lower.
than the
Than the-
lowest ohmic branch, yes?
Correct. Yes.
Okay, and the lowest ohmic branch in this case is 1.5 kilo.
1.5.
So it's got to be something less than 1.5.
Yes.
That's the best we can say right now, since we don't
Right.
walk around with calculators between our ears that can calculate kilos and such. You can certainly say that this REQ number 2 will definitely calculate to be something less than the 1.5 K.
That's
So if we
correct.
put this on our calculator, and let me go hit clear, and let's go ahead and do this calculation. 2.98 second exponent 3, and I'm going to reciprocate that. And I'm going to add that to 1.5 second exponent 3 and reciprocate that equals reciprocate and equals. This is what I end up with. Show me what you end up with.
997.
Great, Rebecca. Almost. Yeah, Pauline is good. Andrew, hold it back just a touch. Gabriel is good. Christian looks good. Rolando looks good. All right. Everybody looks like we're pretty much in there. How's was that Ryan's calculator? How about Andrew's calculator? Working on it. Okay. All right. So we end up with, and we would write down 997 point. What are my last two digits there, Christian?
0.77.
Okay, excellent. It would be 0.77. Is everybody in agreement with that, my friends?
Yes.
Okay, so even though your calculator shows 7678571, you round off to 997.77. Very good. Okay, so this circuit has taken us from the original circuit through a redraw, through another redraw. Have we gotten to our total yet? No, we're not to our total yet. We're still a little ways off. So we still need to calculate our total. And so if we go to do that, what relationship, again, we're looking at the circuit from this perspective on the side farthest away from the voltage source. What relationship do we see between these remaining resistors, Gabriel?
Can you repeat that again?
Yeah, what relationship do we see between these three resistors of this circuit? What's in parallel with what? What's in series with what?
The REQ1 and REQ4 are in series, I believe.
What's happening with R5?
R5 would be too.
Okay, you're saying all three of these resistors are in series with each other?
Yeah.
Okay, how many people agree? Raise your hands. Well, you got a bunch of classmates supporting you, Gabriel. Good job. They are in series because there's only one current path. So if I go to mark in the,
Add them up.
if I go to mark in the polarities here, here, and the electrons that flow, you can see the electrons will flow in only one path. So therefore, these are all in series with each other. Now, how would I redraw my final circuit? My final circuit will show here, will show my voltage source. I'll show here. Do I still mark my point A and B?
Yeah.
Anybody else? Do I still mark a point A and B?
No.
No.
No, I cannot mark a point A and B, and let me explain why. Because point A, if you look at point A very carefully, isn't point A sandwiched between R4 and REQ2? Well, if we're going to combine them, that point disappears. If we're going to combine these into a single equivalent resistance or final resistance here called R total, here's my R total. Point A, which was between these two resistors, has been absorbed inside of the single resistor. If you take a look at point B down here is between REQ2 and R5, and that, since they're combined, our point B has disappeared. So on the final schematic, this guy down here, there is no more A and B. All we have left is our 28-volt source, and all we have left is the sum of these guys in series. So why don't we go ahead and add these guys in series. Bring this guy back up. And watch how this happens on this calculator as each of you discover how to do and utilize memory calculators. This calculator allows me to, oops, come back here. This calculator allows me to add my previous number by simply hitting plus. So it'll take the previous answer, and now I can add all of the giblets of that 997 and add it to 330 and add that to 770. And before I hit the button, let me ask Pauline, what is the total that you get?
I'm still working on it. Hold on one second.
Okay.
2.82. 2.83
2.83
kilo ohms.
kilo ohms. How many people agree with 2.83 kilo ohms? Let me hit a enter and see what happens here. Yeah, I won't quite get that because this is less than 1,000 and these guys come up almost 1,100. So I end up with a less than 1,000 plus 1,100 should be something less than 2,100.
Yeah, I got 210 also.
So this will round out to be 2.10 kilo ohms. So Pauline, you're adding 997.77 plus 330 plus 770. So Rebecca, do you confirm 2.10 kilo ohms?
Yes.
Okay, Rolando, are you good with 2.10 kilo ohms?
Yeah.
Kyle, are you okay with 2.10 kilo ohms? You guys are on mute.
Yes.
Okay, Andrew, are you okay with that number?
Yeah.
All right. Gabriel?
Yeah.
Okay. So we end up with 2.10 kilo ohms. Cool. Now we finally have a total that we can agree upon that we can fill in on our chart. And this guy will fill in right here as 2.10 0.10 kilo ohms. Okay. All right, we still have a lot of things to do, but we've taken the original schematic from 5 resistors to 4 resistors to 3 resistors down to 1 resistor. So have we successfully completed the process of our redraws, bringing us down to the most simplified version of a schematic possible? So far,
Yes.
Yeah.
So now, how do I fill in the rest of these values? We fill in the rest of these values by, first calculation will be our master current here, yes? This
Yeah.
one. So we happen to have a voltage, we happen to have this. So on this calculator, I'm not going to use 2.10 kilo ohms. I'm going to use my previous value. So I'm going to do 28 and divide by, and I can push this button, come up here to call this, hit enter. So now it brings it
I
down
got
here to
13,333.
28. Okay, and then I can hit equals. So what do you end up with on your currents? Question goes to Gabriel. You're up.
I got 13.39.
What's my second digit? 13.39. How many people agree with 13.39? Raise your hands. Pauline, what do you have?
I think I'm getting 13.33.
13.33. Okay. How many people agree with 13.33? Okay, got some raise of hands there. So Gabriel, yeah, you shouldn't be off with your classmates. 28 divide by, you can call it 2100 if you want to enter it the fast way.
Yeah.
I'm going to write down what my calculator shows me. My calculator shows 13.35 milliamps. And it's okay if you're a couple hundredths of a decimal place off from me, because I'm using all my memories, okay? And then when I do a subsequent calculation, I will be using this amount of current with all of its memories. So as long as we're within a couple hundredths of a decimal place of this number, we should all be good. Everybody okay with something very close to this?
Yeah.
All right, let's see how that current flows in the schematic. So here is negative, here is positive. The current flows here, flows here, flows here, and flows here. So my I total works out to be 13.35 milliamps. Now I'm done with this schematic. I can now take this information up here. When I take this information to this redraw, didn't I previously mark negative and positive, and didn't I previously mark arrows for current flow? And what is this current? This current is in fact 13.35 milliamps flowing through these 3 series components. How does this, taking this information of 1335 milliamps up to this drawing, help us fill in what's going on over here? Question goes to Christian. What do you think?
You could do a voltage divided formula, no?
Oh, we could do we can do voltage divider. Sure, we could. Yeah, that's certainly possible. Let's see. I'm looking for another answer. Andrew or Kyle, what else could we do? One suggestion by Christian was to do voltage divider to fill in some of this. What's another suggestion that you would offer to help start filling in this? Andrew or Kyle? Based on this most recent drawing right here that I've just filled in this information. Your mic is, you're muted. Okay, now you can speak.
I would not all be the same, would it?
Well, let's see. Would it? If you look at the schematic, what kind of a circuit do I have here, Andrew?
Series.
Series. And what is the
Series.
same throughout a series circuit?
Current.
Current.
that they're all the same, right? It's the current.
Current is the same. That's correct. So knowing that current is the same, how does that help us fill in some parts of this? You are correct so far. It is series and current is the same in a series circuit.
So that means
If we found the current for R5 and we have the current for R4.
That was Kyle?
the whole thing.
Yeah.
Yes. So as you realize, this is a series circuit. Current is the same throughout a series circuit. Well, hallelujah. You've just agreed that this 13.35 milliamps is the current that flows through R4 and is
Yes.
also the current that flows through R5. So
Yeah.
in this part of our analysis, you have found two original currents for R4 and R5. And we can fill that in. That would be 13.35 milliamps for here. And that would also be 13.35 milliamps for here. So R4's current and R5's current are the same in this schematic. And it is 13.35 milliamps. So two cells have been filled in. So far, this is a very, very good step of going from the most simplified series circuit and taking it up to here. And from here, we will take this further upstairs, okay? But so far, are we in agreement that we have discovered 13.35 milliamps is in fact the current that flows through R4 and R5, and that allows us to fill this in. So far, so good. Everybody thumbs up?
Yeah.
Okay, looks good. Okay, now we're done with this as far as current goes. Now let's go ahead and take this current further up. The current that leaves the source in each case was 13.35 milliamps. Leaves the source is 13.35. Leaves this source is 13.35 milliamps. And interestingly, in this drawing, this current flows and does hit node A. What do you think with this current, what would happen to this current when it hits node A? Gabriel, what do you think happens here?
I want to say it's going to travel down to R3.
Yes, that current will travel down through R3 because there's a wire attached to R3. Is anything else going to happen at node A? Is there any other wire attached to node A?
R5. Oh, it goes R1 too, right?
This is, what's it labeled as?
Oh, RQ1.
Uh-huh. So the current splits at node A. That's the point that I wanted, the verbiage that I was hoping that you would use. The current leaves the source, comes through R4 as 13.35 milliamps, hits node A, and at node A, it splits between two different wires. Part of that current splits down through R3. Part of that current continues on through REQ number 1. So how do I determine how much splits in each of those ways? Ooh, that would be a question to throw out to Pauline. What do you think? What would be one way we could determine how much is the current that actually flows down through REQ, and how about the current that flows through R3? How
You
could we
could use
find that?
the current divider formula,
Mhm.
where it would be IRX equals
Okay, let me go ahead.
over RX.
Okay, let me go ahead and reiterate that. So we have current divider formula, and we will abbreviate that as CDF. And the general form of the formula was, as you recall correctly, IRX is equal to the RT over RX times your I total. So how do we implement this to find out what is happening through R3? How, if we want to find the current that flows through R3, what are the values that we put in here? This is the general form of the formula. The general form of the formula will always be identified this way. but we have to understand how to apply that formula to the unique circumstances that we're presented with. So if we want the current that goes through R3, we write R3 here. So current of R3 is equal to, so what do I use for the numerator, the denominator, and the total? How would I set that up? Question goes to Rebecca.
For RT, you would put 2.10 K ohms over Rx, which would be R3, which is 1.5 K ohms times I total, which is 13.33 milliamps.
Be careful with that, my dear. So the denominator you say should be 1.5 K ohms, yes?
Yes.
Okay, because that is our X. X is the unknown resistor, and in this case, we're given that X is going to be the third resistor, R3. So R3 must appear in the denominator. RT, you're suggesting that we should use the 2.10 K ohm.
No, that's not right.
And Rebecca now realizes, no, that can't be because RT is for the entire circuit. So how do we reconcile, what do we actually use for RT in this formula?
Oh, it's the 997.77 ohms.
Precisely. It was these two combined in parallel gave us a total for the bank. The two resistors form a bank, which is the nickname for a parallel circuit. And the total for these two in parallel came out to something called REQ number 2, which was 997.77 ohms. So that's the value we have to put here, 997.77 ohms, and then multiply by the stated current of 13.35 milliamps. Is everybody clear that we do not use the RT for the entire circuit of 2.10 K ohms here, but we use the RT for the bank of 997.77 ohms? Is everybody clear on that?
Yes.
Why do we use
Okay.
the 1.5
I'm sorry?
kilo ohms? Why do we use the 1.5 in the middle there for the bottom number? Why do
For
we
the
use that one and
denominator?
not the other one?
Yeah. So if we want the current through R3, then we use the value of R3. So here we want the current of R3, so we have to use the value of R3. In a moment, we will look for the current through REQ1, so we will have to use the value of REQ1 in a moment. That's a separate
Okay, I see now.
Okay. So let's go ahead and do the calculation for this. And on this particular calculator, I'm going to recall everything from before. So watch for a moment how things are done on this particular calculator. Even though you may not have the same calculator, but at some point in time when you get used to using memory on your calculators, your calculations will be spot on with this. This shows a stack of previous calculations. My first number is 997.77, but don't I have 997.7678571? I have this number up here. All I have to do is cursor up to that number, hit enter, and that brings that number down as the first value that I'm going to manipulate. My equation says I'm going to divide. So I'm going to hit my divide key. So there's slash for divide. 1.5K, I'm just going to key in very simply as 1500. And then multiply, I'm going to hit a multiply right here. Now I'm not going to use the rounded answer for 13.35 milliamps because I happen to have that fully calculated in detail up here. I will hit cursor up, capture this number, hit enter to bring it down, and then hit equals for my final answer. Can you confirm with your machines, as you would do it, just type in these numbers on your calculator, 997.77, 1500, and then times 13.35 milli, do you end up with something close to 8.88
Yes.
milliamps? And as long as you're, like I say, within a couple hundredths of a decimal place, Rolando, that looks really, really good. And Pauline, Kristen, Rebecca, you show me your calculations. Don't worry about the memory thing. I just wanted to take a moment and show you how it's done on a full. Okay, that looks great, you guys. All right, so we will have for IR3 8 point,
8.
yeah, use the wrong color. Okay, so 8.88 milliamps. Nice. All right. Now, one more current in this bank to solve, and that would be the current on the other side, called IREQ number 1. So IREQ1 is equal to, and I'll write out this first, this must be REQ2 over REQ1 times your I total. And mathematically, this works out to be 997. .77 over 2.98 kilo ohms, and all multiply by 13.35 milliamps. So let's go ahead. And see what this calculates to be. .98, I had it here. Yes, no? Seriously? Oh, interesting. Oh, okay, I know. All right, so go ahead and hit divide. 2.98 seconds here, 3, 2.98, 3, and then multiply by this current. Okay, cool. Pretty small. Yeah. All right, question goes to Rolando. What were you able to calculate for that current?
4.47
Okay, very good.
milliamps.
Very good. Enter, divide by 8 times. Okay, so if you end up with something close to 4.47 milliamps, it's pretty good. So how many people have something close to 4.47 milliamps? Raise your hands. Nice. Show me your calculators. Good job. Good job. Good job. Nice, 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 nice. Very well done, everybody. Huh. Rolando, we have to do something about your calculator.
R1 should be the same.
Hold on just one sec. Rolando, I noticed something on Rolando's calculator. Get into your manual and figure out a way to extend the number of digits on your display, okay? Not now, but after the session is over, okay? Because the more display information you have on your calculator, the better you're able to make the correct decisions in rounding, all right? All right. So there was a question from Andrew. What was your question, Andrew?
So since that one was for the two on R1 and R2, so that I should be the same for both of those, right?
Wow,
For R1 and R2?
That's a great revelation. You're absolutely correct. So this is what Andrew is saying. We just calculated the branch current here as being 4.47 milliamps. And previously we had an 8.88 milliamps here. And when these two currents combine at the bottom, they will add up to be the total current going back to the source of 13.35 milliamps. But his revelation was this current that flows through this branch of the parallel relationship actually flows through an equivalent resistance. And the equivalent resistance was made up of two resistors in the original circuit in series. So this is what we have. We have the current flowing through here as being 4.47 milliamps. And yes, it in fact flows through R2 as well as R1. So yes, your observation of taking this number on our chart and moving it upstairs to here, 4.47, is in fact a correct revelation. Very good, Andrew. Nicely done. So guess what, my friends? You have filled in an entire column of current just by doing current analysis, okay? So we have done, the process is called circuit analysis. We employed a number of techniques. We used redraws as the method, and the purpose was to simplify. We did the simplification, and now we're taking the information back up. The information we take back up in this case is current analysis. So we want to add that to our process. Includes current. I'm getting close to my camera here, so I can't write very well, sorry. So current analysis, and you're going to find that a lot of your circuit analyses can be done with current analysis. You fill in this column, and isn't voltage easy to calculate now? It's nothing more than current times the resistance, right? So let's go ahead and calculate these voltages. So go ahead and start making those calculations. I'm going to be calling out names in a moment for these calculations. Eight, and then here times, that gives me, and then here times, will give me there, and then here will give me, and here times will give me, all right. So I am looking for voltage across R1 by multiplying the current, this current times these ohms, the voltage. Kyle, what do you get for that first voltage?
I got 4.37 volts.
Okay, that's very good. I get 4.38 volts only because I'm using all kinds of memory, but it would certainly accept 4.37 volts. That looks very, very good. Something within a couple hundredths of a decimal place of this number would be fine. So the next calculation, Andrew, I'm looking for VR2. What was your calculation for VR2?
8.94.
Okay. 8.94 is what comes up on my calculator as well. That is a correct answer. Very good. Gabriel, what is the calculated answer for VR3?
13.29 volts, sir.
Okay, so 13.32 volts. You have 0.29. Again, we're within a few hundredths of a decimal place. The calculation is good. I would accept that as being correct. The next calculation, Pauline. for VR4?
VR4 is 4.41 volts.
Okay, I have 4.40 volts. We're good. We're within a hundredth of a decimal place. Rebecca, what was your calculation for VR5?
10.26 volts.
Very good. I got 10.28 volts. We're within a few hundredths of a decimal place. Wow, pretty good, my friends. You did really, really well on this series parallel circuit analysis. What was different about this? What was the same? Well, the procedure is we're going to redraw to simplify. We have done so. Once we get down to here, then we work our way back up, and you'll see each of the examples that we create on YouTube and also previously stated in the week 3 part of, week 11 part of your Canvas will reflect the same methodology. Could we have done the analysis differently? Could we have used voltage divider? Yeah, we could easily have used voltage divider, because right here, if you look carefully, we know the current through the series circuit as being 13.35 milliamp, yes? Could we have calculated the voltage between A and B?
Yes.
Yes. If you have the voltage between A and B, you have found the voltage across REQ1 and R3. And them being the same voltage allows you to calculate a current here, which then allows you to use those currents to calculate individual voltages. So there's many ways of being able to complete the VIR chart in a circuit analysis. What I've always found is if you stay with the current paths, you follow the flow, filling in one column, the current column will allow you to very easily calculate the voltage just by using math. Any questions on this circuit analysis? So far, so good? Okay, cool. We will go ahead and move forward from here, and let's go ahead and put us. I'll take a moment and talk about, let me go to my share screen, share, and let's go to this one up here, share. All right, cool. You can wave to each other. Hi. Okay, so, and I can't bring this forward. Okay, it's only some things I can do, some things I can't do. Yay. See all your smiling faces on the side, because I need this side of the screen. All right, now for quickly, and I'll do a more thorough multi-SIM analysis for you, but I want to take a moment and show us how we engage multi-SIM. Cool. So I have a design and I have a design. Okay, so here's multi-SIM as an interface. And as an interface, it is, I'm sorry, everything is so small on this. It's tiny. My goodness. Can I make this any bigger? View. Zoom in. That's only my worksheet. Okay. Well, I'll probably have to create a PowerPoint to help you out with this. But I happen to have different components in my toolbox. My toolbox, if I click on this, right to here, here's part of the toolbox, and it shows, in this toolbox, I happen to have my master database. Here, I happen to have basic components. What kind of basic components are there? Well, resistor and capacitor, inductor, those are basic components. And Then my next tool in the toolbox right here, placing diodes. I have different kinds of diodes, so LEDs, rectifier diodes, and then I also can place transistor components. So if I were to build a circuit here, I would go back to basic components. And in basic components, I could select a resistor. And as I select a resistor, here is a resistor. So I'm just going to take one. And if I hit OK, it'll pop onto my screen. So here's one, and I'm just going to place it right there. And then hit OK. And then I have a second resistor, which I'm going to place over here. And then hit OK. I will have a third resistor, which I will place over here. And then hit OK. I will have a fourth resistor I will place here. Hit OK. Have a fifth resistor, which I will place here. And then beyond basic, let me go to source. So I want a DC power, this guy here. Take this and place it here. And that's all I need so far. So those are the basic components of the circuit that we've just put together. Now, let me go ahead and zoom in and zoom in further. And let's do zoom in some more. And probably one more time. Okay. These are nice big components. Yay. All right. I click on R1, I hit Control R, and it rotates. I click on R3, I hit Control R, and it rotates. I can take this, move this guy up here. This guy looks pretty good where it is. Line this guy here, take this guy. Line this guy up over here, take this guy. This guy has a positive lead on top. I'm going to Control R. Now I have negative lead on top. And place this guy right over here. And oops, I moved the value separate of the resistor. Sorry. All right, so move this guy. Yeah, go away. I'm not ready to change the value. Okay. This is a good start. Now I'm going to go to connect wires. Now when I go to connect wires, I have a black dot come up here and come over to here, and it becomes a red wire. I will go ahead and take this, come over to here, drop down, make a connection, come over to here, make a connection, take this, come over to here, and make a connection. Click it to make a connection, come over here and over to here, click to make a connection, and do it here as well as here. Okay, so is the building of this very similar to Tina so far? Okay, just a slightly different interface. I can nudge each of these guys to make sure that they are electrically connected, which they are. I can take this guy, oops, select the resistor, move it up, move it down, so it is electrically connected. There, there. Take this guy, here, here. That's good. Take this guy, move it up. So you should do the nudge on all of these just to make sure you have good electrical connection. And so the wires follow. As long as the wires follow, we're good. Let's go ahead and this will be 980. And hit enter. Let me move my camera out of the way. All right, 980. And then we want to make this guy up here 2K ohm. And hit enter. And then we want to make this guy, if I type in 1500, it'll automatically change appropriately for me. Boom. It'll become, no, it doesn't make it automatic. I do have to put in the K. So 1.5K, boom, there we go. And then this guy here is going to be 330, enter. And this guy over here is going to be 770, 770, hit enter. And our voltage source was 28 volts. So 28, boom. Okay, if I wasn't talking so much, this thing would have been built in half the time. So in terms of how MultiSIM works, it works very similarly to the Tina that you've played with so far. What I'm going to do, since I've done this much work, I'm going to do a file save as. So do file, save as. I'm going to save it to a very specific location. I'll keep it here. And this will be, I'll call this Wk-11. And this will be series dash parallel. And this has 5 resistors, yes? 5R. Okay. So we're keeping the naming format similar to what we've used in Tina. That being said, now show you how to make measurements of different things. If I wanted to bring in a meter, I have a variety of different meters: logic, word generator, frequency counter, Bode plot, 4-channel O-scope, watt meter, function generator, multimeter, yay. So the multimeter will come here, and I can then place it to make a connection across any component. So we calculated R2 to be 8.94 volts. If I now connect this guy, and I got to be mindful of my polarities, so negative, positive, negative, positive. So negative is in fact on this side. And let me nudge this wire up, okay, and make the connection over to here. And I can select this wire and nudge it up also, so it's not in the way of my lettering. Then I can go to simulate and run. So everybody, simulate and run. When I do the simulate and run, circuit is not grounded. Oh, they want me to have a ground. Okay, be that way. I will go ahead and insert a ground. Oh, and okay, and I'm going to place it here. There, and get rid of this. And now simulate and run. And as I simulate and run, and if I zoom out, if I do this, I should be able to double click and see my digital multimeter. And although it's really tiny on your screen, and we'll have to work on the zoom characteristics, we calculated 8.94. On my screen, it works out to be 8.938. So guess what? That would round out to be, that would round out to be 8.94. So your measurements of voltages are as easily accomplished as doing things this way. Could we have multiple voltages on here? The answer is yes. So if I come up here and click, I have to get this into the stop mode. You can't build while this is in the run mode. So I'm going to hit stop and then bring in another multimeter and bring in another multimeter and bring in another multimeter and bring in one more multimeter. And we can connect them all up. Remember, the negative side of the resistor is on this side. So if I want to connect this negative lead of the multimeter, I will go ahead and do so right here. And the positive lead, this guy will come on, right there. This guy will connect right there. This guy will connect right there. This guy will connect over to here. And notice that the wire is touching the lettering of R4. I can nudge that wire up, come over to here, and Same here. Now this particular guy, negative side is on this side. Nudge this wire up, bring the whole multimeter up, like so. And now bring this guy over to here, nudge this wire up. Okay, cool. So we happen to have all of these in place, all the multimeters, and let's go ahead and hit simulate and run. And in the run mode, what did we, this was the multimeter for number 1. If I want to see the multimeter display for number 5, this is on R1. R1's voltage was 4.38. And guess what? We have 4.38. We suspected R3 to be 13.32. Double click this guy. Guess what? I've got my 13.32. The R4 we suspected should be 4.40. Double click. Guess what? Measures out to be 14.40. And then this last one over here, double click. We suspected 10.28 and we measured 10.28. Isn't that a thing of beauty? Right there, right there. So this way I'm not bringing any of my original wires.
I'm sorry,
How about that?
can you confirm, sorry, can you confirm the voltage on R4 again? I'm sorry.
The voltage on R4 was XMM4 and XMM4 on this was 13.318. So our calculation of 13.32 is a correct rounding of the physical measurement of 13.318.
Okay.
That was for R3. I'm sorry. Did you want R4?
Yes, please.
Okay, R4 we determined was 4.40 volts. And on the measurement, it came out to be 4.40, looks like 405.
Okay, thank you.
Okay, so that would round
it.
to be 4.41 according to the multisim.
Okay, thank you.
Okay, good. So this is a quick analysis using multisim on the circuit that we just analyzed on paper. And the recording of this session will be in its entirety as we go through another discussion. But also what I've done in the previous discussions, I've broken up the specific topics separately. So if we're done with this, and I'm very happy with this particular portion of our discussion, what I'm going to do is file, because I saved it before. So I want to do another save as, make sure it's going to the destination where I want. The destination is my thumb drive in our 50 folder, and the name was Week-11 series parallel with a 5R. So I'm going to hit save. And yes, I want to replace it. And now it is saved with all of the things around it. Now, when you go to do this, send me your multisim file. All you need to do is to click your little handy snip tool, and your snip tool will come on the screen. So there's your handy little snip tool. And then click on new. Everything goes gray. Oh yeah, actually before you do, I gotta cancel. Hold on one sec. We have one more thing to do. You have to let me know this is you. So we are going to place, so go to the place command, hit text, and you will be creating a text box. So in the text box, you're gonna type and then 4 dash, what day is today? 8-20. All right, so your name will be in there on the text box. You select, deselect, and then now do a file save as, because your final save as has to have your name on it. Yes, I do want to replace the previous one. And so now when you bring in your snip tool, there's our snip tool, and you hit new. And all you have to do is capture from here. all the way down to here. And the most notable things that you're going to capture in this screen, you're going to paste this into a Word document. And what's captured on the screen is the day of the week, the month, the date, the time that it was done, and your name. And that's what you have to do to turn in. So you'll have a fun one to build. Any questions on this?
Yes, I do. I've been trying to download the MultiSIM. It seems to be taking forever. I was just wondering if there's a, if I'm choosing something different altogether.
I couldn't answer that. I've had people in the 51 class have success with this. They've announced that they were able to download it, they were able to install it, and that it is up and running. I'll be able to confirm that when they start sending me back these circuits that are built. I have a previous version of MultiSIM, so I also did the installation, and I also started to create a PowerPoint. And the PowerPoint, let me go to here, let me go to here, and let me go to here and scroll up. And free MultiSIM. Okay, let me bring the PowerPoint onto our share screen. And you can see up to what point I was progressing with the installation, but I had to stop because I had lecture last night and I didn't finish the installation. No, I don't want to do this. Okay, just hit open this and move this guy up here. And okay. So on the link, you would either click this if it were live, or copy and paste this into your address box of your browser. And then what comes up is this screen, National Instruments. And it does say here, free 6-month evaluation, LabVIEW, blah, blah, blah. And you click here and it does, yeah, it also says on their website, free 6-month evaluation, LabVIEW and MultiSIM. So you know, upon clicking this, your next screen should look like this. Now, just because I've gotten to the habit of doing this, they've given me a serial number, and each serial number should be different as you go to do your own load. And I just copied this for future use in case I needed it. Then I click download software. After copying this into the clipboard and clicking download software, the next screen that you see is this one here, and it says National Instruments, which is NI. The same people who build the Elvis boards for us is the same company, and this is one of 2 softwares, the pieces that you're going to install, LabVIEW and MultiSIM. So you just want to make sure that your Windows options are set up properly. Even though I have a 32-bit microprocessor, I mean a 64-bit microprocessor, I find everything takes up less space and loads more easily at 32, and we're never going to run these simulations fast enough to take advantage of the 64-bit, so I just economize and use the 32-bit versions because it takes up less space. Click download. After you click download, the next screen will ask you to create an NI user account. And so you go ahead and create an NI user account, National Instruments user account. And my recommendation is use your personal email. In this case, I used imasample9876@gmail.com. That is a legal email. That's an alternate identity that I use for registering things under imasample. So you create your own, but you want to make sure you have a non-school address in here. And then you go ahead and create your password and you log in. Once you log in, then you should be able to establish, confirm your status. So to complete your account. And so I chose other and then click continue. Then the next slide says your download will now appear here or in your downloads folder. So upon continuing, things on Windows 10 downloads to this corner of my screen. So right there is an .exe file. If it doesn't appear on the bar right above your taskbar, or the last bar of your active window, if it doesn't appear here, it will certainly appear in your downloads folder, okay? So depending upon how things are set up on your computer, you may see the .exe file download here, or you might see it or downloads folder. Wherever you find it, you will click it. And when you click it, you will see this logo pop up on the screen, which means that the installation is beginning. And so just accept the default checkboxes. Don't check anything more than what's defaulted. You will see this option here, hit next. When you hit next, you will see this window. Oops, come back here. When you will see this window, and don't change anything here. Don't select anything, just hit next. When you hit next, you will get to the EULA. What is a EULA? E-U-L-A. Gabriel, what's a EULA? EULA. I'm looking at the EULA. This is the EULA on the screen. So what is a EULA? The EULA is an end user license agreement. That's the nickname given to this. And you click accept, and then you hit next. And then the next screen, if you happen to have an error message come up, and I have slight error, because like I say, I've already had MultiSIM downloaded into my computer. It detected it, so hit next. And then what happens, if there's any more next screens, just keep hitting next, and boom, there's the install. The green bars are happening. And yes, it does take a long time. I started this, I think before 5 o'clock, and it didn't finish before my 6 o'clock last night for this upper green bar to reach all the way to the end, to the finish line. So I don't know if mine ever fully installed, and I don't have any more slides after this, but this is what I have so far, and I'll be happy to post this in Canvas so you can follow these steps. But it's fairly intuitive, the steps that you click in order to do the install.
I've gotten that far to where you are.
Okay.
And for whatever reason, now I have quite a few recently added in my application. Which of these do I choose?
Okay, so in your applications, let's see, I can't do it on this screen. Let me take a look. We would look under NI. Oh, I do have the other N. I do have MultiSIM 14.2. Isn't that interesting? Cool. Okay, so what I am going to do, let me give you a snip of this. Not this guy here. Not this guy here. Not this guy here. Not this guy here. Here is reduce this. I need my snip tool, but I don't want it full screen. Okay. Oh, come on. Be nice to me. All right. So I want here and NI, and let's see if I can do new. Oh man, it won't let me do it. Maybe new. No, it won't let me split this function. Okay. Let's see, let's do a different share. Let's go ahead and let's go to here. And what I'm going to do is, if I hit share, screen one, hit share. So now you're looking at my primary screen, I think. Yes, no?
Yeah.
Do you see my desktop or you see my smiling face?
You see your desktop.
Good. Okay, wonderful. So here I'm going to hit start. And as you can see my desktop, I will scroll down, and under NI, I've got a slew of stuff. So under National Instruments, I've got MultiSIM 13.0, MultiSIM 14.2. So it did install. And so you want it should appear here in your pop-up Windows menu, and under N, National Instruments, you will simply select MultiSIM 14.2. So let me click on this guy and see if this guy's working for us. Even while the other one's running in the background. Well, there's MultiSIM 4.2. Cool. Hello. And it begins 7-day trial. There's no, I don't want, okay. So here, enter activation code, serial number. I had a serial number. Yes. So let me come back up here. That goofy little serial number that I had on the screen before. I know what I need to do. This is the completion portion. Okay, I'm not going to activate this right now. What I'm going to do, though, is since I happen to have a serial number from before, I will type in that serial number here, and that serial number should give me beyond the 7-day trial. And I will finish the rest of my PowerPoint based on what I'm looking at here, but I don't want to do that now. So you'll see the PowerPoint in its completed format sometime later tonight, tomorrow morning, something like that, depending upon when I'm able to get to it. But this is the serial number that appeared way back at the beginning that I said I make a habit. If they identify some kind of a number, and let me bring this right back here. Okay, here's my PowerPoint. And remember in my third slide, there was a serial number that was identified. I say copy your serial number. It goes to your clipboard, click download software, or write it down if you don't remember. But definitely use that serial number, and that hopefully should unlock us past the 7 days. So this is, at least on my machine, 14.2 is in the process of finishing its installation. And like I said, I didn't finish it last night because I had classes I had to conduct. And I think the finished portion here on my screen is just simply to enter that serial number and then activate, and it should be good for what they've stated it as being a 6-month license.
Hey,
Did that answer your question?
Yeah, I'm trying to download it right now, and I was clicking on it, and I got a "we're sorry, ni.com is temporarily down for site maintenance."
Well, then you're going to have to wait for them to. You're going to have to wait till their site maintenance is done, or just start the link again on a separate window. Use a different browser. That's probably what I would use. Were you doing that in Microsoft browser? Or were you using Chrome, or were you using Firefox?
Chrome. I think I'm going to use Firefox.
Okay, so what you do is you copy this URL that was given to you in the email, and you paste it into the address box. And then I have Firefox as well, so I will go to Firefox, double click. Okay, there it is. Put it in the address box, hit paste. No, I don't want this to be default, thank you. Hit paste. Come on, paste. Copy, okay, and go back to Firefox. And paste. There it is. Hit enter. And let's see if the site is under maintenance here as well. I suspect it should be. Hit OK on the cookies. And then make this window a little larger. And scroll down. to yes, I agree. So were you able to get to the agree screen like I just did?
Yeah, I'm typing in my information.
Okay, all right. So it looks like you're on your way. It looks like it's working through Firefox. I don't know what's happening with respect to Chrome, but at least with it, it doesn't matter which browser you use as long as you can download it. So this is where you create the user account. I've already used I'm a sample 9876. I've already used my own name, so I can't create any more. But this is where you would do. Okay.
It works.
Okay. So okay, and when you progress with this, it should continue working fine. Are there any other questions regarding this before I go on to the next?
Yeah. Is this also just for a Windows program, or would it work?
Yes, this is only for Windows. It doesn't work for Mac unless you have a Windows emulation program on your Mac.
Okay.
Okay, and some people who have set up their Mac with different partitions, where they've partitioned a portion of their hard drive space to accommodate Windows programs, then they're successful at implementing this. But just straight into a Mac, no, it's not compatible straight into a Mac. So you have to do some other things. So whatever your solution was that you used for Tina would be the same solution that you would use for a multisim. Did that answer your question, Christian? Yeah, probably not what you wanted to hear. I'm sorry, but yeah.
No, that's fine. I borrowed a PC, but it's really slow, so I'd rather not use it. But I mean,
yeah. Well, what I've demonstrated on the other share screen with the multisim, that will work just fine even with a slow PC. Okay, so there's no anything about that whatsoever. What we're asking multisim to do for us is not any high-speed analysis, so not to worry. Your other PC will work out just fine. Any other questions regarding the multisim?
So even though I have Tina, now I have to download this one too?
Well,
Multisim?
yes, because as we're going, this offers us more power. This was not available to us until last night. So if it was available to us before, then I would have not asked us to do the download of Tina. But since this was not available to us before, Tina is a really, really good free circuit analysis. This particular one has more power and is also what you want to get used to using, because this is what we actually have installed in school.
Oh,
So the answer to your question is yes, Rolando. Yes,
yes.
even though you have Tina, you want to switch over to multisim and get this particular screen that I've built for you set up.
Okay.
And any other questions regarding multisim? Okay, let me do one more screenshot here. New, because I know I need it. I will do this here, do this here, do this here, and I need to do a save as, so file, save as a JPEG, and put it into 50, and put this into one space. Oops, come here, come on. One space, sim series dash parallel 5R I'm a sample. Cool. Okay. Now I can dispense with my clipboard. Now I can shut down my multisim, and that is done. Okay, onward. More other things. Superposition theorem. Superposition theorem. Yeah, we can do this. Actually, one circuit analysis is enough for today because I need to talk about other things. But let me touch on this here. Let me get onto Canvas. So this PowerPoint File. Save. Okay, so I can close this PowerPoint. I will modify it in a little bit. Mozilla, I can go ahead and close. And MultiSIM, I can go ahead and close. All right, so I will go ahead and do a different share. Okay, let me walk you through. Okay, everybody should be able to see my Canvas screen. Yes?
Yes.
Cool. And on Canvas, what we're going to do is let's go to our class and talk to you very quickly about a couple things, and I need to get into capacitors. So we have week 10, we have week 11. So on week 11, capacitors, lecture photos. So go to lecture photos, and on superposition 1, superposition 2, superposition 3, these guys are images, and you'll download them like so. And let me open the first one and see what I've got here. Okay, so this was a lecture that I had done in a different school. That's okay, but I want to point out to you, yes.
Yes.
Can everybody see the image okay? All right, so what I want to point out to you is this particular part right here. Let me move this image and zoom this. To here. If you take a look at this, what's unusual about this circuit is there's 2 voltage sources. What do you do with 2 different voltage sources? Because each one of these is trying to move electricity in a different fashion. So this one has a negative plate on top, a 38-volt source. This one has a negative plate on top, 50-volt source. It looks like the electrons that are coming from the VS1 are going to come up through R1 here and hit this node, yes? It looks like the electrons leaving VS2 are going to come up and go through R2 and hit this node. So it looks like we're going to have a clash of electrons at this node. So how do we do a VIR analysis on something like this? And the analysis is really quite simple because you've done this analysis before in pieces. So what I mean to say is there is a step 1. Let me move this out of the way. There is a step 1, and step 1 engages what? A redraw. What are you redrawing? You redraw with one source, what? Removed and replaced by a what?
Wire.
Wire. So I'm going to remove VS2, and where VS2 was, I'm going to replace it with a wire. So now what do I have left? Now what I have left is 3 resistors and 1 voltage source. We did this last week. This is peanuts. This is not hard to reconcile, this one simple circuit. Where do I start this simple circuit? I start over here where can you see my cursor moving? My little arrow? This is where we start. Remember, on the side of the circuit opposite the voltage source. When I'm looking at this wire, what kind of a relationship do I see of the components on this wire? This wire is attached to an 8 ohm R2, right? Is there anything else on this wire before I hit those nodes? None.
No.
So that one wire, that R2, has what relationship with R3?
Same current.
They're in
Series.
Are they in series? Do they share the same current?
Parallel.
They're in parallel. Remember, the definition of parallel was, do the leads on one side meet at one common node? Right here. This upper lead of R3 and this left-hand lead of R2, are they meeting at this node here? Yes?
Yes.
And are the leads on the other side, so look at the R2 on this side, follow this wire all the way down through here. Is it connecting with a different common node with the bottom lead of R3? Yes, they are. So even though they're not drawn to be in a picture looking like they're parallel, electrically, they are in parallel with each other. So we can reconcile these two into a single REQ. This would not be 10 ohms, would it? You don't just add 8 and 2 because they're parallel. So the total must be less than 2 ohms. When you go to do the calculation, go to calculation right now, 2 parallel with 8. 2 reciprocal, 8 reciprocal, what do you get? Show me your calculators. Nice. Okay, Rebecca, Gabriel, good. No, you forgot to reciprocate the. You have a different value in there. Whoever's whether it was Kyle's calculator, it was not correct. It is R3 is a 2 ohm resistor, so you're putting 2 ohms in parallel with 8.
Oh, okay, okay.
Here, yeah, 2 ohms parallel with 8. Gabriel, your calculator? You're fine. Christian? Okay, good. Yeah, Pauline's fine. Rolando's good. So Andrew and Kyle, I need to see your calculators.
625?
No.
No, I'm still off. Okay.
What you do is 8 reciprocal
8 reciprocal.
2 reciprocal equals, hit reciprocal one more time, and then hit equals. What do you get?
Okay, 1.6.
1.6 ohms, and look at my screen. If you look at my screen, do I have
Yeah,
R2 and
1.6.
R3 in parallel giving me 1.6 ohms? Yes? Cool. And then
1.6.
yes, 1.6 is correct for these 2 guys in parallel. So now I redraw these 2 guys in parallel to a single equivalent. And now what do I have? Don't I have a simple series circuit? And with this simple series circuit, I've got 4 ohms in series with 1.6. So my total ohms here is what? 5.6 ohms, yes?
Yes.
I have 38 volts. Can I calculate a current? I
Yeah.
can calculate a current, okay? So do I have enough information to transfer this current into, actually, we'll hold it there. Take a look at step 2. Step 2 is to redraw with the other voltage source shorted. So VS1 has been replaced by a wire. VS2 comes back into play. And now I still have 3 resistors, but with a single voltage source. Can I reconcile these into a simple series circuit? Do I have an R1 that's 4 ohms? Is it, what relationship with R3? What is the relationship between these 2 resistors now?
Parallel.
These are parallel. And if I have 2 ohms parallel with 4 ohms, what is their combined ohms? I use reciprocal method, and I should end up with, what do you calculate? Rebecca, what's your number? Rolando's a good number. Gabriel, what's your number? Okay, that's good, Pauline. I can see that now. Thank you. Do we end up with 1.33 ohms?
Yes.
Okay, we should end up with 1.33 ohms. And we now have a simple series circuit. So when you get to view this on your own systems, my friends, when you view this on your own, you can increase the zoom quite a bit and be able to see the circuit analysis. So here's my 1.33 ohms for my REQ, and that is in series with 8. So what's my total ohms in this case? My total ohms for this particular guy works out to be 9.33 ohms on this side, allows me to calculate a total current. From here, you will do your current analyses. And so we're using, the key to the solution is with current analysis. So you have R1 in the first example demonstrating a certain current, it'll demonstrate a certain voltage. I have to work this through to you. Anyway, when I work one through with you, look at this for now. I will work this out with you if we have time at the end of the session today. If not, we'll hold off on superposition, the solution, or maybe I'll just create a work through solution on Zoom and then record it on Zoom and then deliver it in Canvas or YouTube. How many of you have been able to look at the YouTube videos for the circuit analysis for series, parallel, and parallel series? Raise your hands. Gabriel, have you been looking at my YouTubes?
Yep.
Okay. Rebecca, have you seen the YouTubes?
No, but I'll look at them today.
Okay, yeah, they're under, and I gave everybody the links. And so those particular YouTubes that are specific to circuit analysis are not a re-recording. There's one YouTube that's a recording of our entire session. And then I broke up the session into different parts that were specific to different tasks. So you will see a Tina YouTube, you will see 2 separate YouTubes that are specific to parallel series analysis. You will see a separate YouTube that is series parallel analysis. And when I get a chance to chop this guy up, you will see the one that we've done earlier as yet one more analysis, okay? So definitely refer back to the YouTube videos because hopefully you will find them helpful to you. The best way for us to peek at that, let me just give you a quick peek. Okay, so here's YouTube. And under YouTube, you can look under Frank Coe, and under Frank Coe, just click on my smiling face and then go to videos. And the most recent videos are the ones that are on top, and these are the ones that are pertinent to all of us. So what was the path? You go to YouTube, you type Frank Coe, you click on the icon with my smiling face, and then on my home page, you click on videos, and you can see pertaining to us, we have Co-Guy parallel series with 4 resistors, number 2, Co-Guy series parallel with 4 resistors, Co-Guy parallel series with 4 resistors, and then I will have the 5 resistor one posted up here. Here's the Tina tutorial. I will also have the MultiSIM tutorial. Everything will be under Co-Guy. So you can refer back to these over and over and over again to help you with the method and the process of how we go solving these circuit analyses from A through Z. Any questions on these so far? And where to find these? Okay, done. That being said, let's go back to stop share and let's go to click the camera. All right, need to talk to you about capacitors. Okay, everybody can see my my white paper. Capacitors. These are devices exhibiting capacitance. So that begs a question. If we go back for a moment to our electronic components, electronic concepts chart, we would have a concept called capacitance. The symbol, so this is our concept. The symbol for capacitance is given as C, the symbol is a capital C, and the units of capacitance are given as farads, F-A-R-A-D-S, farads. I'll give you a little more light. Farads. And the unit symbol is farads with a capital F. And of course, we have a brief definition. And the brief definition for capacitance would be, say, 1, ability to store charge. So it's given as the ability to store charge. The name of the device is a capacitor. And what is a capacitor? A capacitor is conductive sheets separated by a special insulator called a dielectric. So in the category of insulators, what are insulators? Insulators materials that do not conduct electricity. So can you give me some examples of some materials that you encounter that do not conduct electricity? Question would go to Andrew. Give me one type of material that does not conduct electricity. We know copper does, we know steel
Rubber.
does, iron, aluminum. What's that? Andrew?
Rubber.
Rubber is a good one. Excellent. And Kyle, give me another example.
Plastic.
Plastic is really good, like plastic. Yay for plastic. All right. Let's see, Pauline, can you think of another insulator? Rolando, Gabriel, Christian, I just threw that out there in general.
Glass.
Glass is an excellent insulator.
Porcelain.
Yes, your ceramics is under a general category called ceramics, which would include certainly porcelain. Okay. Okay, these are all very good examples of rubber, plastic.
Wood.
Wood is a very good insulator, sure. If somebody's holding on to a live wire, a best way to save them is get a broomstick or something and whack their hands so that you're not conducting yourself to the live wire, and the wood is not conductive. So by using the piece of wood, hopefully you can detach their hand from whatever they're holding on to that's causing them shock and injury. So yeah, these are really, really good examples of insulators. Now, we said that these are conductive sheets that are separated by a special insulator called the dielectric. Well, we're not going to use rubber, we're not going to use wood, we're not going to use glass. There also happens to be air, and there also happens to be pure water.
I was just about to ask about pure water.
Yeah, pure water is a good insulator. You won't get electrocuted with pure water, but if it's muddy water, ionized water, you're standing in that puddle and there's a live wire in the same puddle, you're toast. But pure water, you're safe. All right, so dielectric, the special type of insulators that are used in the construction of a capacitor would be some of these items. And some of these items would be plastics.
Paper, no?
And paper. Paper is an excellent one here. Let's add paper here. paper. And paper, so plastics, you would encounter mylar as a type of plastic. Another type of plastic, tantalum, is another type of plastic material. So there's different kinds here. There's also air that's also used. And another one that's very popular is ceramics. And another one would be electrolytic. And that is a paste, and often with paper. Okay. And so that being said, the capacitors that you have been given in your kits have been this guy here we talked about, and this guy here that we've talked about. So these are two examples of capacitors that you have been given. This one happens to be a ceramic capacitor, and ceramics is a very common way of building resistors. Resistors are a ceramic compound that happens to have conductive powder in there. It's like an iron dust in there, and depending upon the concentration that varies between ceramic and the conductive material will determine how much resistivity this particular fellow has. The ceramic capacitor is designed in such a way that we do have separate conductive plates in there, and they're separated by the ceramic material. So let me give you an example here. And the same thing with the electrolytic. So when we say conductive plates, I want to show you that we want to be thinking about the plates as being something like this. Here is a plate. Here is another plate. Here is another plate. And here's another plate. So let's say I show 4 plates, and I go to attach a wire onto one of these, and then I have a wire on the far end. And so these are conductive plates. And sandwiched in between the gaps would be a variety of different kinds of what type of material? What word did I use here? It's called dielectric. Everybody say dielectric?
Electric.
Dielectric. And so this particular electrolytic capacitor can be sheets and sheets and sheets of conductive material with the paste in between, and then they roll it up and put it into a little package like so, where one wire is attached to one plate on one end of the roll, and the other one is attached this way. So in your textbook, and I'll assign the appropriate pages in your textbook for you to explore this, but the textbook goes into greater detail of the construction of how and material, various materials that goes into capacitors. What I'd want to share with you at this point is how to deal with capacitors in a circuit. So capacitors in series, and then in series they would look like this. So a pair of parallel lines is the common symbol that's used for capacitors, and we would name the C1, C2, and C3. And if I have these 3 in series, suppose this one happens to be 100 microfarads. This one is 300 microfarads. And the last one happens to be 470 microfarads. So we use the micro symbol. Remember, it's kind of like a cursive U with a long leading first stroke, and a capital F for the unit of capacitance, which is expressed as farads, and the symbol is F. So C1 is identified as having a value of 100 microfarads, C2 is 300 microfarads, C3 happens to be 470 microfarads. Well, it turns out, whoops, Rebecca dropped off for a moment here. Hold on, sorry. Okay, hopefully she can come back on. Are you back on with us, Rebecca? You dropped off for a moment. Back on, yay, Rebecca's back on, good. All right, so we have 3 in series. So C total for capacitance in series is different than resistors in series. You know, resistors in series, we just add up the numbers. Capacitors in series work differently. Capacitors in series will be with the reciprocal formula. It will be 1 over C1 plus 1 over C2 plus 1 over C3. So if you're going to use reciprocal formula, I'll write this down, reciprocal formula. As we've applied reciprocal formula to parallel resistances, one thing that you can conclude for sure, CT, comma, in series, comma, must be less than lowest cap in series, period. What is my lowest value cap in series right now? Happens to be the what? The 100 microfarad capacitor. And if I go to calculate the reciprocal relationship of these 3 values, I will have a total that is less than 100 microfarads. So that you can say for sure. The capacitors in series, calculation-wise, are kind of similar to using reciprocal method for parallel. So let me key this into the calculator. I would encourage you to do so this way, 100 and your whatever you use to get to the exponent. For some of you, it is at EXP. For some of you, it is second EXP. For some of you, it's whatever exponent. And this will be a change sign. So for some of you, change sign, because this will be a change sign 6. So there's your 100 micro. 100 EXP negative 6 is 100 micro. What do you do with that? You have to reciprocate that, x negative 1. Then you're going to add it to 300 on your calculator, EXP, change sign for the negative 6, and you're going to hit the reciprocal here, and you're going to hit plus. Then you bring in the last capacitor of 470, and it will be EXP, change sign, 6, and you have to reciprocate it. Then you hit equals, you hit reciprocal one more time, and you hit equals one last time. So if you go to do that keystroke sequence, and again on your own calculators, instead of the change sign being in parentheses, some of your change sign keys might be, what would they have? A plus / minus, like that, okay? So however it works on your calculator, you know that it's got a total less than 100 microfarads. So I'm going to bring in my calculator and move this over to here. Light it up, clear the display, and I will go ahead 100. I have to use a second key on mine, double E, change sign 6, reciprocal, plus 300, second double E, change sign 6, reciprocal, plus 470, second double E, change sign 6, reciprocal, equals, reciprocal, equals. So I have a number And what is it that you all calculate? So I see Gabriel's. Oh, that's a good number, Gabriel. What is the power of 10 that you have on the very end? I can't see that. Your microphone.
-6.
-6. Very good. And Rolando, what is your power of 10 at the end?
-6.
Good. Pauline, you see a -6 as the power of 10 on yours as well? Okay, good. Looks like everybody's spot on. So yes, if I go to do all of this, I will end up with, this is going to be equal to 64.68, looks like. 68 micro and capital F for farads, okay? So are we in agreement with respect to that value? So far, so good? Good. That's how you reconcile capacitors that are in series. Capacitors in parallel are way easier. So let me show you that. Caps, I will abbreviate now, in parallel will look like this. How will they look? Okay. C1, C2, C3. All have the same values as they did previously. This was 100 microfarads. This was 300 microfarads. And this was 470 microfarads. So my C total in series will behave with a formula by simply adding them. It will be C1 plus C2 plus C3. So CT in this particular case, just simply by adding these 400 works out to be 870 microfarads, yes? Is all of the writing pretty clear for you on your screens? I know I moved the camera around several times, I'm sorry. So in series, we have this value, and in parallel, in parallel, we have this value. In series, we had this value. Let me outline a few things here. And then the formulas that we use. Here's the formulas that we use. There. And here's the formula that we use here. Okay. Good with series and parallel capacitances. So far, so good. Thumbs up if you're okay with this. Good. All right, Rolando. Thumbs up. Christian,
Yes.
thumbs up. Yes, are we good with this so far? Andrew and Kyle? I see one thumbs up. Where's the other thumbs up? Cool. All right, outstanding. So this is a brief introduction into capacitors, but now with this newfound information, if you were to see capacitors in this fashion, so let's go ahead and now do this. Caps in parallel series. So if I show you this and I'm looking for C total, and here is a measuring point, here is a point A, C1, C2, point B, a tap like so, and bring this guy over to here. C3, C4. Okay. So if you were to see this, is this a parallel series circuit? Fundamentally, do we have series components here and series components here that will allow us to simplify? So knowing what we've done before, I'm still looking for CT. We'll have up here a point A. I still have a branch coming over to here, come down. I have a point B. This guy is the series relationship between these two guys put together. What kind of a label would I put on this capacitor here between point A and B? So the question goes out to Rolando. What would I call, how would I label this?
In series, so that's the reciprocal.
I would calculate it that way, but I'm looking for a label before I do any numbers because I didn't present any numbers yet.
C1 times C2. A product over sum.
Oh, you could calculate, again, we would calculate it using product over sum. I was hoping you would call this CEQ1.
Okay.
And I'm hoping that we call this CEQ2. Just like we had an REQ1, we had an REQ2, we have a CEQ1, and we have a CEQ2. Okay, very good. And how do I determine the value of CEQ1? CEQ1 was C1 in series with C2. That's a series relationship. Actually, so as not to cause any confusion, we write it this way. C2. Mathematically, you are correct. We would do the reciprocal method of 1 over C1 plus 1 over C2, or we could also do C1 times C2 over C1 plus C2. We can engage product over sum as well. So whichever method we use, this plus is not an addition symbol. This simply means in series with. That's what that plus represents. We're not going to use it for addition. It means from an equation standpoint, they are in series. So let's go ahead and pop in some values here so that you can calculate. So just for simplicity, let's go ahead and make all caps is equal to, let's say, 580 microfarads. So each one of these is 580 microfarads. So if I'm going to use reciprocal method to calculate my CEQ1, and I have two of these that are 580 microfarads, so 580 microfarads, 580 microfarads. I have another 580 microfarads over here, and 580 microfarads here. If I got a pair of these in series, then their equivalent must be less than that. Are you reminded of a shortcut?
Be in half, no? Like
Yeah.
1, 2.
Yeah, are you reminded of a shortcut? We had a shortcut. Remember, back with resistors. back with resistors. If I had back with resistors when using reciprocal method, one shortcut was equal to something called product over sum, which is what we have over here. This is product over sum. So I'll put a little star here, put a little star here. But we also had an alternate shortcut. Alternative shortcut would be given as C, whatever that particular capacitor is, whatever value that is, we'll simply divide by N. So N stands for number of identical value series caps. So do I have identical series caps in here?
Yeah.
And the value's given us 580. And how many do I have in series? I have 2 in series. So what is 580 divided by 2? Isn't that 290?
290.
290. You could do that using mama's calculator between your ears, right? So let's go ahead and double check that with a scientific calculator. Let's clear. So let's go ahead and actually key in 580. I'm going to do the reciprocal method. Second exponent -6. So that's my first 580 microfarads. I'm going to hit reciprocal and hit plus 580. Second exponent -6. That's my second 580 microfarad capacitor. Hit reciprocal, hit equals, hit reciprocal, and hit equals. Guess what? Don't I end up with 290 microfarads? And isn't that what we determined would be the result of the shortcut method? So this guy works out to be 290 microfarads. And by the same token, since those are the same there, this is also 290 microfarads. Are we okay with the simplification process so far? Now, the task is to bring this to a C total. So we simplified 4 capacitors down to 2 capacitors. Now we have to simplify these into a single total. So my CT right here, here's my point A, here's my point B, and right in between here will be my CT. And CT was equal to CEQ1 in parallel with CEQ2 in parallel with. That's what that symbol represents, just like this represents in series, that little plus up there. So how do I calculate capacitors in parallel? I have 290 microfarads on this side. I have 290 microfarads on this side. Use the reciprocal method on this, yes or no?
No, you just add them.
Just add them, correct. Because if you remember from our previous sheet, we had capacitors in parallel. The total for capacitors in parallel was simply adding the values. We have capacitors that are drawn in parallel. Electrically, they're in parallel, but the total is determined by the sum. So previously we added 100, 300, 470 gave us 870 microfarads. Here we happen to have 290 microfarads and 290 microfarads. So guess what we ought to do? We just simply do this. My CT is going to be equal to, mathematically, 290 microfarads plus 290 microfarads, and that will give me 580 microfarads. Yes?
Yes.
Are we okay with this?
Yes.
Mm-hmm. Okay. Are you ready for series parallel with capacitors? Okay. Okay. Series parallel caps. So in this particular instance, let's go ahead and draw it this way. I am looking for C total. Could somebody mute their microphone if you're making a lot of noise near the microphone? Yeah, because there's a lot of, some kind of noise was leaving to your microphone. So just be mindful of that. Thank you. Here's the cap. C1. Here's the cap. Here's another cap. I'm going to make this one C2. Make this C3. Here's another cap. C4. C5. Here's another cap. Do C6. Sure, why not? We have 6 caps. Okay, this one's going to be 300 microfarads. This one's going to be 300 microfarads. This one's going to be 300 microfarads. This one's going to be 100 microfarads. This one's going to be, I think, okay, all right, keep it simple. This one's going to be 100 microfarads. And this is also going to be 100 microfarads. I'm looking for a C total. You are looking for a C total. So a very close friend of mine, a professor from Nigeria, Mr. Nimine, was asked by his grandma. His grandma asked him a question. The question was, how does a man eat an elephant? Elephant's a pretty big animal. Your jaw is only so big. So how does a man eat an elephant? And the answer to the question was 1 bite at a time. How do we solve for C total on something like this that looks rather intimidating? Hopefully it won't be by the time we finish the explanation. If you use the same method to approach this as we've done before, this is your C total. Imagine that this is also your voltage source. How do you analyze this? You go to the point farthest away, and the point farthest away is over here. And you look back at the circuit from this perspective. And let's go ahead and label this a point A. Let's go ahead and label this a point B. So what do you see when you're looking at that wire? What do you see as a relationship between some components that are on that wire? Rebecca, what do you think?
They're in series.
What's in series? Can you be more specific?
C4, C5, and C6.
Does everybody share the same observation?
Yes.
C4, 5, and 6 appear to be in series.
Right.
So if they appear to be in series, can I replace those three with a single equivalent capacitance?
Yes.
So in my redraw, and I will do this right below the first one, I'm going to redraw. I'm going to have my C1. So C1 is still there. I'm going to have a point A. My C3 is still going to be here. I will have a point B, and my C2 is still going to be here. So C2, these guys are 100 microfarads. This is 100 microfarads. This is 100 microfarads. And then over here, I can replace this. Oops, sorry. I started drawing a resistor, didn't I? Funny guy. Okay, I'm going to replace this with a single capacitor, which we will name CEQ number 1. And this was C4 in series with C5 in series with C6. So how do you reconcile capacitors that are in series? Mathematically, what do you do? How do I determine what the value of CEQ1 should be? Question goes to Gabriel. What do you think? I have these three in series. What did we do with capacitors in series previously? What method did we use? Look at my screen.
C program formula.
My screen. Capacitors in series, which is what we had before. The formula we use is this. What was the method? What's it called? What am I pointing at? Can you see my screen? Your microphone's off.
Oh, reciprocal formula?
Reciprocal formula, correct. And so whatever these values are in series, you know that the total of these three in series must be lower than the lowest branch.
Right.
So it must be less than 300 microfarads. So could we calculate CEQ1 using reciprocal method?
100.
One method equals reciprocal. So if I use reciprocal, that would be CEQ1 would be equal to 1 over C1, 1 over C4 plus 1 over C5 plus 1 over C6. And if you use reciprocal method, yes, this gives you a value of 100 microfarads, correct?
Yeah.
Now, that's one method. Can anybody suggest an alternate method? We don't have two, so we can't use product over sum. But
Yeah.
since we're using reciprocal, was there another reciprocal shortcut we could use?
We can do CX over N.
Precisely. Another reciprocal shortcut that we had talked about before would be your CEQ1 would be equal to your CX over N. N meaning the number of capacitors that share that same value. How many capacitors share the same value of 300 microfarads? So 300 microfarads divide by 3. Won't that also give you 100 microfarads? And isn't that a faster method of determining what this value is? So this works out to be 100 microfarads for CEQ1. Is everybody okay? You can always rely on reciprocal method when these guys are in series, or you can, if they happen to be the same, let's go ahead and use the shortcut. So good job there. Thank you, Rebecca. Any questions on this so far? Now, we have taken 6 capacitors and brought it down to 4. Our viewpoint is still from this perspective, looking at this corner, and we happen to see a capacitor here. And what is the capacitor CEQ1? What is its relationship with C3?
Parallel.
They look like they're in parallel. So could we combine these into another equivalent capacitance?
Yep.
And when you go to do so, let's go ahead and bring in my tap here and bring this guy here. This guy comes here. So my points A and B here are found A and B over here. My capacitor here at this point, just like I had a capacitor over here, and we darken that, make it a little easier to see. This will be CEQ number 2. And CEQ number 2 was equal to C3 in parallel with CEQ number 1. So that means this is equal to 100 microfarads in parallel with 100 microfarads. The other parts of our circuit are the same. C1 is still 100 microfarads. And C2 is still 100 microfarads. So the question becomes, what does this calculate to become? How do I calculate capacitors that are in parallel? What was the formula method that we employed earlier?
Addition.
Yes, because so if we go back to our first diagram, capacitors that are in parallel, it shows them in parallel. The total for them in parallel was to use a simple addition. We add those values together. So previously we added 100, 300, 470, gave us 870 microfarads for them being in parallel. We should be able to do the same here. We have 100 in parallel with 100. So all we have to do mathematically is 100 microfarads plus 100 microfarads gives us 200 microfarads is equal to CEQ number 2. Are we all in agreement with that so far? Okay, so this is 200 microfarads. Okay, do we have, are we okay with this so far? Are there any questions so far? All right, so the next thing becomes, what do we do to calculate a CT? Because we're still ultimately, we're looking for C total. So C total shows what relationship between these 3 capacitors. C total is equal to C1 in series with C2 in series with C3. So mathematically, how do we reconcile values that are in series for capacitors? What did we do for series capacitance before? Capacitors in series, as shown here. We used what formula? Reciprocal formula. So if we're using reciprocal formula, let's go ahead and calculate the reciprocal of these 3 values. So this would be equal to, since I happen to have no more space at the bottom of my paper, oh, I can do it. So you can do it. All right, so CT CT is equal to 100 EXP negative 6 reciprocal, and we're going to add that to 200, do this in sequence, 200 EXP negative 6 and reciprocal, and plus 100 EXP, change sign 6, reciprocal, equals, hit reciprocal one more time, and hit equals one last time. So if you follow on your calculators the appropriate keys to give you the sequence, then the result should work out to be the reciprocal plus 200. Okay, I've got a number. Good, okay, cool. So 100 recip plus 100 recip plus 200 recip. Really? Rolando? 100, 100, 200. I don't think I get the same number as you do. Rebecca, do you have a number yet? That's very good. Gabriel, Pauline, do you have a number yet? Gabriel, that looks really good. Rolando, you want to recalculate, please? Pauline, Christian, what do you have?
I got 40 microfarads.
Okay, Andrew and Kyle. Can you show me on your calculator what you have?
We're working on it.
Okay. Yeah, Rolando, your first number was in need of adjustment. Your first calculation was in need of adjustment. So the CT, long and short of it, the CT works out to be 40 microfarads for C total. Okay, by the time we're all done. Okay. And Rolando, were you able to recalculate that? Pauline, how are you coming along with that calculation? Yeah, kind of. Does it say 40? Yeah, there. Okay, I can see it now. Thank you. Yeah, it's just catching the glare off your screen. So it was, I'm looking at glare. I couldn't see any numbers. All right, Andrew and Kyle.
Almost there.
Almost there.
Almost
Okay.
there.
Yeah, whichever method is specific on your calculators to get this done, this is the method. So to summarize, this is an example of resolving series parallel capacitors, their relationships based on the initial formulas. So again, so to summarize, capacitors are those devices that exhibit a property known as capacitance. The concept is capacitance, the symbol is C, units are farads, symbol is F, ability to store charge. The device that gives us this characteristic is called a capacitor. Conductive sheets separated by special insulator called a what? Dielectric. Insulator materials, we talk about a variety of different
I just
kinds.
didn't know
The
that.
very specific kinds of capacitor insulator materials that are used as dielectrics would be these: mylar, tantalum, air, any type of ceramics, electrolytic paste. The example of the conductive plates here, your book actually does a much better illustration of all of this. Now, what your book doesn't do is show you the next 2 pages. And the next 2 pages in our notes today are capacitors in series, capacitors in parallel. So for capacitors in series, they behave in series to calculate a total that is like parallel resistors. We use the reciprocal method. So whenever you see capacitors in series, whatever their total works out to be less than the lowest cap value. And it says so here, CT in series must be less than the lowest cap in series. And we worked out the keystroke sequence for you in our notes all the way through for this particular sequence. And then capacitors in parallel, we draw them in parallel, we use the same values. The formula is as if they were resistors in series. We use the summing method, C1 plus C2 plus C3. These add up to give us 870. The first combination circuit we encountered was caps in parallel series. And if they are in series here and they are in series here, remember we use the reciprocal method. An alternate.
This has a lot more power.
I'm sorry, what's that?
Oh no, Kyle and I, we got our math problems. We got it for you.
Oh, okay, let's take a look. Yes, and hold it with a little less glare. Okay, I can see them. Perfect. Good job, guys. Nice, nice. I'm glad you were able to get those. Thank you so much. So back to our notes. If I have caps in series, we use reciprocal method, but we also happen to have reciprocal method engages a shortcut known as product over sum. So if we use 580 times 580 over 580 plus 580, we'll end up with the same value. If we use reciprocal, we'll end up with the same value. But interestingly, since these happen to be identical values, we can use a fast shortcut, which takes identical value components and divide by the number of those components. So 580 divide by 2 that have the 580 value gave us 290. These resolve to be a pair in parallel at 290, and parallel capacitors you simply add. That gives us a C total of 580 microfarads. Then if we go on to the last discussion of capacitors, capacitors in series parallel arrangements, and this one we really did something quite a bit more elaborate, which I'm glad we were able to do. Simplified 6 capacitors down to 4 capacitors down to 3 capacitors, ultimately to a single total value. And the methods were as explained. So I'm glad you were able to get all the way to here. Whew, okay, that's a full session, my friends. I think what we'll do is the entire session has been recorded. The entire session will be played back on a YouTube, but I will break up the different parts for specifics. The capacitor discussion will be one specific YouTube. The circuit that we had done earlier will be a separate breakout. Of the superposition I will have to do as a separate one that I'll record between now and the next time we meet for you to view and play with superposition. So this keeps us on track. In this particular week, we happen to have some additional online reading material for you all to do. So I will be selective of that. You will see references to week 6. Ignore any references to week 6 because remember what I did was we copied the shell from an 8-week course into our 16-17 week course. So if you see any references that in our week 11 part of Canvas referencing week 6, just ignore the week 6 reference. But it is all good with capacitors and superposition. Wow, I commend you all for doing such a great job in hanging together with us for all of this. So one more thing I need to do on my roll sheet, and that is to make sure I check that Rolando is here with us. So we have Rolando, Christian, Rebecca, Gabriel, Andrew, Kyle, Pauline, 1, 2, 3, 4, 5, 6, 7. And I have 1, 2, 3, 4, 5, 6, 7 on my alternate screen. Fantastic. Wonderful. Okay, so let me change this view. And go to, I think, move my camera out of the way. And let's go to gallery view. All right. So now we're on the gallery view. I take a picture of all of us in our smiling faces. Sure, Co. With what? Okay. Let's bring out this camera. This will work. Yay. All right. So for the dean's happy with this. Christian, with that window behind you, you are like a silhouette. Can you lean closer? We can see your happy, smiling face. There you are. Fantastic. Hold on there for one moment. Smile, everybody. Wave.
Yeah.
All right, fantastic. Got you captured. Before we part company, are there any questions as to moving forward, what it is that you need to do? Download and finish the installation for MultiSIM. I will have circuitry for you to build in your circuit board that you will do the analysis, use MultiSIM. You will have homework pertaining to series, parallel, and series, parallel, series capacitors. You will also have a video that I'll construct regarding superposition theorem that I would like, as soon as I am able to get it constructed, that you all will make some time to view it before our next meeting. And I think that that's a pretty good recap of what we have to do. That's a lot of work between now and then. Any questions that any of you have? You need to unmute your microphones at this time if you have any questions.
Questions?
Yes, no questions? Questions? Gabriel, you okay?
I'm okay.
Rebecca, you all right? Okay.
Yeah.
Okay, good. Pauline's okay. Rolando, you all right?
Yeah.
Okay, and Kyle and Andrew, Christian? Okay, all right. So with that, my friends, thank you very much. Great session. And we will continue. All right. Have a wonderful week.
You too.
Take care now. We'll see you. Stop the recording somewhere here. Yep.